Welcome, everyone. Thank you for joining us today. My name is Natalia Martin, and I'll be your moderator for this webinar. Today, we're talking about network engineering. Our panelist is Andrew GINTER, the VP of Industrial Security here at Waterfall Security Solutions. Before we start, I'd like to mention a few things. This webinar is being recorded, and you will all receive the recording link within the coming days. There will be a Q&A session at the end of the webinar. Please submit your questions in the Q&A panel at the bottom of the screen at any time during this session. We will try to answer all the questions at the end of the webinar, but in case we're out of time, which happens, we will follow up with you individually and answer it via email. And with that, Andrew, turning the stage over to you.
Thank you, Natalia, and hello everyone, and welcome to the webinar. Thank you for joining us. I'm going to talk about network engineering. This is, in a sense, it's a new discipline. Nobody's talked about this kind of thing for a long time, but these are all, in a sense, old techniques that are being pulled together into a new body of knowledge that is becoming part of the cyber-informed engineering body of knowledge. So let me start. If you haven't seen any of the recent oh, I have the wrong slide up here. Well, rats. Okay. It's too late to change. You're gonna have to imagine a line moving up towards the right on the slide here. If you haven't seen any of the recent webinars that we've put on regarding our 2023 threat report, the threat report shows that the threat environment changed about 4 years ago, and very few people realized. For the whole period, 2010 through 2019, imagine a red line on the bottom of the chart here, 2010 through 2019, not much happened. We're talking about bouncing around between, zero events, zero attacks in a given year that shut down physical operations, and maybe 4 max. Big names like Norsk Hydro and Triton and Stuxnet were all part of that sort of flat line where threats to physical operations were mostly theoretical. We just did not see a lot of shutdowns or equipment damage or other consequences of cyber attacks. And what's happened since 2019, in 2019, there were like 4 or 5 attacks that had physical consequences. In 2020, there were 18. In the next year, there were 23. The year after, there were 57. Does anyone, this year we're thinking we're probably going to hit 130, give or take. Does anyone think we're ever going to go back to a year like 2018 where there was 1 attack with physical consequences in heavy industry and manufacturing? Attacks in the public record. I don't think we're ever going back. The world has changed. Attacks are more than doubling annually. If, at the rate they're doubling currently, they're increasing tenfold every 2.5 years. If this continues, we're going to see 100-fold increase in 5 years. In the year 2027, if this trend continues, we're probably going to see 4,500 or 5,000 attacks, taking down 15,000 to 20,000 sites. This is a train racing towards us down the tracks. I'm not sure we can build a wall big enough to stop that train. I think we have to get off the tracks. And the good news is that there's a way to get off the tracks. There's a way to think about this problem differently. And that is, it's called a number of different things. I call it software engineering. A more technical term is cyber-informed engineering. There's a strategy document that came out of the Department of Energy. Idaho National Labs did the work with funding from the U.S. Department of Energy. And it talks about a strategy for increasing the degree of participation of engineering teams in the cybersecurity solution. What does that mean? Well, the classic example of engineering grade protection, the classic example is, a mechanical pressure relief valve. Imagine that we are technicians in an old school power plant, a coal-fired power plant. 6 generating units. Every generating unit has a 4-story tall boiler. It's a massive boiler. Imagine that every one of us listening here, every one of you is the technician responsible for those 6 boilers. You replace sensors that have failed. You calibrate the sensors, you calibrate the system, you have the gamma ray testers to test the corrosion. You know, these boilers are your baby. We work, you and I work every day inside of the kill zone of a worst case boiler explosion. If one of these boilers explodes, we never see kids again. How would we like to be protected from a boiler explosion caused by a cyber attack that overheats the furnace under one of these boilers? Would we prefer a spring-loaded valve so that if the pressure in the boiler becomes too great, it forces a steel plate against the spring deforms, the steam escapes, and there's no explosion? Would we prefer a spring-loaded valve, or would we like a longer password on the PLC controlling the boiler? Most of us, I think, would prefer the spring-loaded valve, or 3, because these things do wear out. Some of us might say, I want both, thank you. I want all of IT cybersecurity, and I want these engineering mitigations. And that's perfectly legitimate as well. This is, you know, if a boiler blowing up is a truly unacceptable consequence. And so the strategy is talking about engineering grade mitigations. I'm going to say one more word on engineering grade, and then I'm going to switch to network engineering, which is a subset of the strategy, but it's the focus for this webinar. What is engineering grade? What are engineering grade protections? Well, again, imagine, I mean, I'm hoping that most of us have heard about the 1940 Tacoma Narrows Bridge disaster. If you haven't heard about it, Google it. There's a video. It's instructive. Tacoma Narrows was one of the first very long suspension bridges. It was a new design for bridges back in the day. The problem was that back in the day, the engineers really did not understand harmonic frequencies. A stiff breeze, not a hurricane, just a strong breeze came up and started the bridge vibrating, like a children's swing set. You push the child and it comes back, and if you push the child again at just the right moment, it builds on the swing, and you push again, and a stiff breeze came up that started pushing on the bridge at just the right frequency, and the bridge started vibrating, started wobbling to the point where it tore itself to pieces. So imagine that the engineering community has figured out a new way to design suspension bridges. It costs 1/3 the cost of today's suspension bridges. Massive savings. The problem with the design is it's absolutely riddled with harmonic frequencies. The smallest breeze, people walking across the bridge, that cadence of walking starts building up and the bridge tears itself to pieces. And so the engineering community has designed active dampers into the bridge, hydraulic dampers, multiply redundant power supplies, artificial intelligence controlling the dampers. The bridge feels rock solid as we walk across it, as we drive across it, because the dampers are sensing the vibration and actively counteracting it. How happy would each of us be driving across that bridge if we knew that the design engineer hoped that if a cyber attack targeted the AI controlling the dampers, that we hoped that we could detect that attack before it compromised the AI? How happy would you be driving across that bridge every day on the way to work if you knew that the design engineer hoped that if we detected the attack in time, we could scramble an incident response team fast enough to defeat the attack before it compromised the AI? How happy would you be knowing that the design engineer hoped that if the response team was too slow and the attack compromised the AI, that the response team could recover functionality fast enough to prevent a disaster? Hope is not what we expect of the engineering community. When an engineer designs a bridge, there's and public safety is at risk, there's a strong expectation that the bridge will hold the specified capacity, the specified load for, in a given environment, in a specified environment, for a specified number of decades. That's the expectation we have of engineering. Hope is not good engineering. So what we're looking at in the network engineering world is a subset of cyber-informed engineering. Cyber-informed engineering is it's not, they don't use these words in the strategy, but I've been on these the calls, the community of interest calls, where the body of knowledge is starting to come together. The phrase that's used in the calls is that cyber-informed engineering is a coin with two sides. One side is cybersecurity. Teach engineers about cybersecurity. The other side of the coin is engineering. Use engineering techniques to take cyber risk off the table. Here's the thing, though. Where is the mechanical overpressure valve in the NIST cybersecurity framework? It's not there. Where is it in 62443? It's not there. These are all, where is it in ISO 27001? It's not there. These are all cybersecurity standards and frameworks. The overpressure valve is an engineering mitigation. It's not cybersecurity, but it can be used to address cyber risk. So here's the thing. Network engineering, where does it fit? What happens if that valve engages and the steam escapes and there's no explosion? What happens? The sensors all go off and say, the boiler overpressurized. Nobody died. This is great. Engineering prevented the thing from exploding. Engineering prevented anyone from dying. This is good. What happens? What's the next thing that happens? The systems or a person, bang, triggers an emergency shutdown of the plant. That should never have happened. We're not going to start this plant up until we understand why it entered an unsafe state, and we've taken measures to make sure that never happens again. The spring-loaded valve is a last-ditch stopgap. And so the lights go out. Wait, this is critical infrastructure. Yes, safety is number one, but reliability is number two. Keep the lights on. It's great that nobody was killed by a boiler explosion, but the lights went out. Society doesn't have power. So that is also an unacceptable consequence. How do we prevent the lights going out? Well, the only way to prevent the lights going out from a cyber attack due to an attack on the boiler there is to prevent the attack getting into the system in the first place. And this is network engineering. Safety engineering protects life and limb. Protection engineering protects equipment, prevents equipment from shaking itself to pieces. Network engineering protects reliability. It's engineering grade protection for networks. So what does that look like? Here are some examples. The first example is, vibration. So this is from EPRI, the Electric Power Research Institute. They published this in about 2018. It's a method. It's not all of network engineering. It's one example of a network engineering approach. The question that EPRI was asked, and EPRI is a research organization. They have, I don't know, dozens or hundreds of PhDs on staff researching questions in the power grid. The question that was asked of EPRI was, look, we have these steam and gas generators, massive devices, $300–400 million each, massive investments. And we want to optimize maintenance because maintenance costs on these big things. And if we can make these devices last longer between service outages, we get more value out of them. So what we would like to do is use the industrial internet, monitor the devices, send the monitoring information out to the internet, to the vendor, who manufactured the turbine, have them use their artificial intelligence and come back and tell us how to maintain the devices optimally to save money so that we can produce cheaper power. I mean, what are the top three priorities at most physical operations? Number one is safety. Don't kill anyone. Don't cause an environmental disaster. Number two is reliability. Keep the lights on. Keep gasoline in the pipeline. Keep drinking water in the taps. And number three is efficiency. Do all of this efficiently so that society can afford to buy the electric power. So society can afford to pay for the water coming out of the taps. Efficiency is important. So the industrial internet gives us efficiencies, but the power companies were saying, but I worry that a bad guy is going to get into the turbine vendor and download malicious firmware into my devices and attack my control network in the power plant. I've got a heavily defended power plant. This connection out to the internet lets information out. It also lets attacks back in. How do we deal with this? So EPRI put some PhDs on the problem and came back and said, here's what you do. Here's the method. Get the monitoring devices, the vibration monitoring devices. Do an engineering study on them. Convince yourself that these devices are monitor only. They're physically monitor only. Not that there's a switch that you can switch from monitor to control. They're monitor only. All they can do is monitor. And then they said, put them on your turbine and connect them to the IT network. Put them on a DMZ on the IT network. Or, if you want, stick a SIM card in these things and put them straight in the cellular network. Whatever you do, do not put them on the industrial network, because then if malicious firmware comes in, it can attack everything else on that industrial, on that control network. Put it on its own network. Now, what happens if the cloud service is compromised? You can send new malicious firmware in. It can mess up with your maintenance schedule. It can cost you money. It won't destroy the turbine. It won't cause, a safety incident, because the monitoring devices are not able to send any signal into the control network. They're not connected to the control network. They're on their own network. Great. I get the benefits of, the savings from, optimal maintenance. And the fact that these equipment is connected to the internet does not pose a threat to safety or reliability. So there's one example of network engineering. Here's another example. It's generally useful. It came from a US Department of Defense publication on how do we do building automation. If we have a building automation system, let's say we got a campus of buildings, 17 buildings, 3 of them have got classified stuff inside of them. And so the entire building, every piece of electronics in the building is at, kept at a classified level. But the control system for the entire campus is not classified. How can I let information from the classified buildings flow out to the main control system, the unclassified control system, without putting the classified buildings at risk? And so that's the question this publication answered. But where I see this technique being used in the wider world, most of us don't have classified networks. Where I see it being used is in safety systems. We want to monitor the status of our safety systems. Are they working? Have they tripped? If they tripped, what's the reason for the trip? All of these signals we need to come out of the safety system, but most of us do not want to connect the safety system into our main control network through a firewall, because firewalls can be breached. Firewalls are not engineering grade protection. So what can we do? How can we get signals out of the safety system into our main HMI without putting the safety system at risk? Well, here's an example. The same technique works. They say, look, you've got PLCs in the safety system. You've got PLCs in the classified buildings. Run a handful, 5 or 10, 4 to 20 milliamp loops out of the secure zone, the safety zone, into the control zone. Connect those 4 to 20 milliamp signals into a PLC on the control zone. Now you can send a single value over each of those wires. You can single value from the safety system, hello, I'm still alive, out to the control system where the PLC can sense the value, a 1 or a 0. Yes, I'm still alive. Now, the HART protocol can piggyback on top of that, can piggyback messages. Messages can contain attacks. Turn off HART. Buy hardware that does not support HART. Now, all you can do is send one signal back and forth. It can be a 1 or a 0. Yes, I'm alive. A 1 or a 0. I've tripped. I was the one that shut the plant down. An analog value saying, here are important values that you want to monitor that I'm reading. A handful of values, 5 or 10. And now, I defy you to send malware into the safety system through a 4 to 20 milliamp loop that's sending one signal. You can't do it. So this is the engineering grade way to prevent attacks from entering protected systems like safety systems, while still monitoring those systems so we know what's going on. For the record, it is a little expensive. in my understanding, each of these loops and the endpoint, the devices you have to have on the endpoints of the loops, they add up to about $500 per signal. So if you have 10 signals, that's $5,000. You can afford that. If you have 1,000 signals, we probably need a different solution. That solution becomes very, very expensive. But for example, in a peaking plant, this is the power plant that gets a signal once a second or once every 2 seconds saying, give me a little more power, give me a little less power, so we can track the power consumption in the grid with power production from the plant. That's one value coming across, the set point for how much power to produce. This is a solution that would work, for safety systems, for peaking plants, anywhere that you have a small amount of analog or, ones or zero, very small amount of information that needs to be safely communicated with engineering grade confidence that no cyber attack is going to come across as well. Air gaps are old school. A lot of us don't like to think about air gaps, but I had three things to say. One is if you absolutely need it, air gaps are engineering grade. Nothing gets across. At least nothing online gets across. Offline is another animal. So we're talking about network engineering. I'm not talking about USBs and people engineering. That's a different question. That's, chapter 8 in the new book. I'm talking chapter 5. So let's talk network. Air gaps say there's no network connection. There's a few things here. One is that, they can be expensive because now we cannot access the information that we need to realize business efficiencies. This is the main reason air gaps have disappeared. Second thing I want to say is, saying that air gaps are engineering grade is only true for real air gaps. What's a real air gap? A real air gap is a network or a device or a system of devices that have zero way to exchange any kind of signal, any kind of online signal with any other system. That's an air gap. The problem is there's practitioners out there saying, I have an air gap system and it's connected through a firewall. And I'm going, how can you have an air gap system that's connected through a firewall? Oh, I've configured the firewall so that my protected system cannot send messages directly through the firewall to the internet. That's not an air gap. No, yeah, it's an air gap. No, it's not an air gap. There are people out there using the word incorrectly. So be very cautious. If someone tells you, I have an air gap network, they're probably wrong for two reasons. One is that most networks that used to be air gap long since have been connected. And if you think they're still air gap, it's because you haven't done a connectivity audit to see what is the modern connectivity. And the second reason they're probably wrong is because they're using the word incorrectly. They're using the word to mean no route to the internet. That's not an air gap. So if you hear people talk about air gap networks, challenge them. Have you done a connectivity audit? Are you talking about connectivity to the internet, routable connectivity instead of any connectivity? All that said, there are circumstances where people still use air gaps. It's more rare now, much more rare now than in the past, true air gaps. Everything from the simplest. I mean, I have a power drill with a little liquid crystal display. It's got a CPU inside it. Does it have a network connection? No. Okay, isolated CPUs in very isolated circumstances, of course they're air gap. How do you hack the CPU in my power drill? You have to take the drill apart. You have to physically touch it. So you still do see air gaps occasionally. Here's an example where a safety system is air gapped, the network diagram, but the plant operator can still see the values that the safety system is manipulating. How does that work through a real air gap? Well, the safety system is a bunch of PLCs, a bunch of safety instrumented systems that are on the network that has no connection to anybody else. Actually, in this example, there's a unidirectional gateway. Again, I got to look harder at these diagrams. I wanted to give you an example without any connection. So ignore the gateway. I'm going to come to that in a few slides. Ignore the gateway here. Imagine the safety instrumented system is completely air gapped. But the plant operator still needs to see the values in the safety system. How do you do that? Well, you put an HMI on the safety network. You run the wires from the safety network to the plant operator's workstation, physical workstation. You put up a display and a keyboard and a mouse, and now you can interact with the safety system through that display. The rest of your displays, the projection screens on the wall, the other screens and keyboard on the operator's desk, are part of the main control system. And so even though the safety system is air-gapped, the engineer can still control the safety system by physically touching the keyboard that's electrically connected to the safety system, can still see what's happening in the safety system. And I'm going to come to unidirectional gateways in a moment. But if you want other things, not just the plant engineer on the HMI to see what's happening in the safety system, you can, of course, put a unidirectional gateway in there. But I'm going to come to that in a moment. So these are 3 network engineering techniques. Some common themes. Where do we use network engineering? Do we use it everywhere? Well, no. I mean, does a small shoe factory deserve network engineering? Well, what's the worst that can happen if a cyber attack gets into a small shoe factory? Can anyone die? Well, what's the biggest threat to life and limb in a shoe factory? It's the robots. It's the machines that are producing the shoes. The robots have, yellow lines taped around on the floor saying, stay outside of this. Sometimes they have, infrared sensors that say if somebody steps inside the line, they cut the power to the robot. If a technician is going to go and fix the robot because something is worn out, what's that technician do? They go to the power control for the robot. They take the lever, they switch it over to off. There's no more power in the, we've cut off all of the power to the robot. They take a lock out of their pocket. They lock the lever in place. They put the key in their pocket, and now they can crawl into the robot to fix what they like, confident that the robot is not going to start up on them while they're inside because of a cyber attack. So that's safety is done. It's off the table. What's the worst that happens in a small shoe factory? Cyber attacks get in, they mess with stuff. They steal information. We have to call in experts, pay through the nose to bring in experts on an emergency basis to clean up the mess. It'll cost, $3 million in a small shoe factory. We have to lay off our workers for a week. They go on unemployment insurance. We call them back after a week, and then we have to schedule overtime to make up lost production. So, we have to pay again an extra $5 million overtime to make up the production. The total is an $8 million hit. We can buy insurance for that. Arguably, we don't need network engineering for that, because the consequences are acceptable. What's the worst case consequence in a coal-fired power plant? Boilers blow up, people die. The lights go out, the nation doesn't have electricity. What's the worst case consequence in a gasoline pipeline? Well, if we interrupt the flow of gasoline, the nation doesn't have the fuel that we need to, drive, to transport food into large population centers. That's a real problem. What else can happen? Well, in the worst case, if you manipulate the pipeline, you could trigger a hydraulic hammer that causes the pipeline to rupture. Now gasoline's in the environment, there's explosions, these are all unacceptable physical consequences. What's the worst that can happen on most business networks? You steal, the bad guys steal personally identifiable information. They mess things up, and you have to again pay gurus to come in, and it takes 10 days to bring everything back. Again, business consequences. Where we see network engineering being used routinely, intensely, is at consequence boundaries. Okay, the worst case consequence. Imagine that every CPU in your industrial network, every CPU is under the control of the enemy. Every CPU is giving the worst possible instructions to the physical process. That's your worst case consequence. If the worst case consequence, like for a small shoe factory, if the worst case consequence is acceptable, buy insurance. You probably don't need network engineering. When the worst case consequence is unacceptable, we need engineering grade protection. Now, we can get engineering grade protection for safety, but we can't really get engineering grade protection for liability unless it's at the boundary of the network. We've got to put network engineering in place to protect reliable operations when unreliable operations, when failures of the process are unacceptable. So you use network engineering at the boundary between the business network with acceptable consequences of compromise and any network where the worst case consequences are unacceptable. That's the place we use network engineering. There is an exception. The one exception I've observed is that businesses with very expensive physical processes that are not necessarily, let's say we're manufacturing automobiles, and our plants are producing 10,000 vehicles a day. How much money is that? Well, I don't know. Your average new car costs what? $50,000. 50,000 times 10,000 is $500 million a day. If we're down for 3 days, that's $1.5 billion of lost production. Even if the business is big enough to say, I could swallow that, is it good business to swallow that kind of loss? We might want to use network engineering on very expensive processes, just because network engineering is really quite cheap. And, it's just foolish not to put engineering grade protection in for a process that's that expensive, that's going to cost us that much if it goes down. So if the consequences are unacceptable, we use network engineering. If the consequences are just so big that, it's just silly not to use network engineering, we use network engineering. This is where we see network engineering deployed. And by far, the most common, now I've given you 3 examples. I gave you the EPRI example, the 4 to 20 milliamp loop example, they call it analog signaling example, the air gap example. By far the most common network engineering, the most frequent network engineering measures we see deployed are unidirectional gateways. And you've probably heard me say this, but I'll give you the 3-minute introduction if you've never heard of a gateway. The gateway, NIST 882, the new standard, was just released a couple of days ago, in fact. The last 2 versions of the standard have defined the term unidirectional gateway. They define it as a combination of hardware and software. The hardware is physically able to move information in only one direction. It's engineering grade unidirectionality. There's a circuit board, in the device on the left that has a fiber optic transmitter, a laser. There's a circuit board on the right that has a receiver. There's a short piece of fiber on the front that's almost exactly 18 inches long, almost exactly all of the time. You can send from the inside circuit board to the outside, but it's not physically possible to send anything back. With a firewall, if you configure the firewall correctly, we hope the firewall should not allow any attacks into the industrial network. With this device, it cannot send anything in. It's engineering grade unidirectionality. And, the software, in a sense, is where the magic is. The hardware is engineering grade. The software makes copies of servers. The software sort of makes everything work. If we have an OPC server, a Pi server, anything that we need on the industrial network, anything that is a source of data that we need to consume in the business network, the software logs into that data source, logs into Pi, Aviva Pi, username and password, nothing tricky, asks for all of the latest data, everything new since the last time we asked a second ago. We get back a snapshot of 20 megabytes of data. We push the data through the strange one-way hardware. And on the other side, the software logs into the enterprise Pi server, inserts the data. Now we've synchronized the 2 servers, usually to about, plus or minus 20 milliseconds. It's done on an event-based system. But the point is that all of the data that is allowed to be shared with the business is out in the enterprise already. Anybody on the enterprise, any person, any system on the enterprise who needs the data can ask the enterprise Pi server or the enterprise OPC server or the enterprise MQTC, whatever we're replicating here, can ask the enterprise copy for the data and gets the same answer as the live system would have given. But now no question can be sent back into the industrial system to put that system at risk. No question needs to be sent because all the data that's allowed to be on the enterprise is out here in the copies already. So that's unidirectional gateways deployed most often at the IT/OT consequence boundary. There's a lot of recent standards have been talking about, the TSA talked with their pipeline standard, their new pipeline regulation, security directive, the new rail security directive. They've got a whole bunch of special things you have to do at the IT-OT interface. Why are they talking about the IT-OT interface? Because it's a consequence boundary. This is the heart of network engineering. You do things differently at consequence boundaries. I've said some things about firewalls that, I've said some things about IT security that you might have taken as negative. It's not true. Firewalls make perfect sense. Firewalls are needed. They're absolutely needed inside of industrial networks. They're absolutely needed on business networks. They're absolutely needed at the IT-OT interface of small shoe factories. But you need something stronger. You need network engineering at a consequence boundary, at a boundary between a network whose consequences are unacceptable. That one place, that's where we see unidirectional gateways deployed most routinely. And it gets more complicated than that. Here's a more complicated example. Imagine that we're a small manufacturer, the shoe factory, or let's say we're a large shoe factory. We're so big we want to do some network engineering. A large shoe factory is producing pallets full of shoes. Lots of different orders in progress. Every pallet of shoes that comes off the line automatically, 8 shoes a second flying into the packing process, has to be labeled. Okay, that pallet's going to be lifted, carried into a warehouse. It's going to be organized in the warehouse. When the train comes by or the truck comes by, the right pallets of shoes are going to be put on the truck to go where they're going. The labeling is vital. Okay, if we lose the ability to label the shoes, we can take the shoes into the warehouse and we'll never find them again. And here's the thing, labeling, it could be custody transfer systems in pipelines. It could be container tracking systems in shipping. This was the Maersk scenario. What if, a lot of these systems live on the IT network, not in the OT network, because where things are going, which customer they're going to, that's tracked by the IT systems. So if we study our networks, what we find is that we do not have 2 networks, one that is safety critical and one that is, a business network. We in fact have 3 networks. We have the safety critical OT network, the gasoline pipeline. We have the business network that's running our business, and we have a reliability critical subset of the IT network. Some of the IT systems are critical to reliable operations. We cannot operate the physical process unless we have those IT systems. Those IT systems are not just IT systems. We cannot manage them as IT systems. They have to be managed as reliability critical assets. So, concrete example, the labeling system. If ransomware hits the IT network and the labeling system goes down, we have to stop the factory. It doesn't matter how big the factory is, we have to stop it because we can't keep track of the shoes anymore. So what do? How do we deal with this? Put a unidirectional gateway in place, put network engineering in place to protect the safety critical network. Information comes out, nothing goes back. Great. But the reliability critical network, we've got to be able to send new orders in there. There's got to be, we're probably going to put a firewall on that network, but we got to manage that network. We got to use some of the network engineering ideas to manage that network. And one of the ideas in network engineering is tracking dependencies. If we're going to put the gateway, so the safety, the main manufacturing network behind the gateway, nothing gets in. That system cannot depend on an IT system. We've completely separated them. This is good. The factory keeps working no matter what cripples IT. But here, if, let's say the ransomware cripples everything, what's the incident response team do? They make a beeline for the labeling system because they know, they've been trained. This is critical to operations. We have to keep the factories running. They make a beeline for the labeling system. The labeling system's, let's say, hosted on a virtual machine. With the press of a button, we've got a clean image of the labeling system back up there. All of the labeling transactions that came in from IT over the last 10 years have been written to write once optical media You cannot change the media once you've written to it. And so now what we do is we say, well, when was the last virtual snapshot taken, the last clean snapshot? Ever since that moment, replay the transaction logs to bring the reliability critical component back up to the current day, the current moment, and start it working again. And now, the factory's been down for an hour and it's back up again. We didn't have to lay anybody off. We hardly noticed. This is an acceptable outage. What that means, though, is that the labeling system cannot depend upon the IT system. A lot of the mechanisms that, for example, the TSA has ordered pipelines and rail systems to put in place to manage dependencies make sense here. The labeling system has to be able to operate independently. It cannot depend on the Active Directory system from IT, because Active Directory might still be crippled. We haven't brought that up yet. It cannot depend on DNS and IT, because the DNS server might be crippled. It cannot depend on any IT function. It has to be managed as an independent resource, just like we manage the control systems as independent resources. So if we look hard at our systems and ask, what is the worst case consequence of compromise? We may be surprised. Of course, there's generally safety and reliability consequences on the OT network. When we have unacceptable reliability consequences on the IT network, we have to take steps to reduce those consequences to acceptable consequences. And a lot of those steps are the same techniques that we see used in network engineering, like dependency analysis. One more thing, I've said, unidirectional, one way out, nothing back. I've said disconnect your industrial internet from your control network so that no compromise can propagate. I've said, air gaps. I've said analog signaling. The problem is that we always need to bring something back into the industrial network from time to time. We need production orders for the shoe factory. We need, peaking instructions for the power plants. We need contractual requirements for the pipeline. All of this has to flow into these networks from time to time. We need maintenance instructions. Remember the EPRI example. We send the information out, the AI, the expert systems figure out optimal maintenance, and then those instructions, we have to act on those instructions somehow. How do we do that? What's the network engineering way to prevent information that's entering our critical systems? Okay, critical means unacceptable consequences. How do we prevent information flowing into there from crippling those systems? It's hard. We have to look really carefully at all of the information entering a critical system. And it's easiest to do that if the incoming information is abstract. What does that mean? Well, let's say the EPRI example. The expert system has figured out that there's 73 adjustments. I mean, these turbines are infinitely adjustable. There's 73 adjustments, new PLC set points that have to be sent into the turbine. If the turbine system said, here's 73 new set points, off you go, and you and I personally looked at that list, could we figure out if this is a safe configuration of the turbine, or if the turbine in fact is going to shake itself to pieces? There's no way I can look at 73 registers and values and make sense out of them. If instead I get a text message saying, Andrew, the turbine is going to need maintenance. It needs to be adjusted. Call the site. Set up a remote screen view. Work with the site to get these adjustments done. That abstract message is coming back in, as being filtered through my brain. Okay, I can go and verify that in fact there is a vibration anomaly on my systems that are connected to the turbine. I can act on this information. I was working. I'm hoping. I'm starting to work. There's a mining committee in strip mines. What's the problem in strip mines? There's explosives. You loosen the rock, and then this massive shovel comes. It picks up 750 tons of ore and drops it into a truck. The truck holds one shovel of ore, 750 tons of ore. The massive truck starts driving. You've got a whole mine full of this going on. drives the ore to a primary processing place inside the mine, where it's shaken and cooked, and a little bit of acid dripped on it to get the good stuff out of the ore. It's primary processing at the mine site. Every shovel is different, though, and so the sensors are sending the information about every shovel into an expert system. The expert system is coming back saying, here is the optimal way to save money processing this ore so we get the most out of it at the least cost. Again, if that comes in as 700 PLC registers, how can we tell if that is a safe configuration of the primary processing facility? If instead that instruction comes in as, let's say, an XML file, and the XML file says, okay, you've got a bin that's rotating. The bin there's only 5 safe rotating speeds. Instead of putting a PLC register in there saying 73 RPM, if you put in the number 5, the fastest, or number 3, the middle speed, there's 5 speeds, rotating speed 1 through 5. All you can express are safe config. Let's say you've got 2 angles for the bin. You've got low and high. That's it. Instead of sending the angle 73 degrees. Instead of sending the angle in, you send in the text LOW, low, or the text high, HIGH. Those are the only 2 values the system is going to understand. It's not possible to orient the rotator at an unsafe angle, because all you can express. So this is the key. If information is entering your system, network engineering demands that information be as abstract as possible, so that ideally people can look at it and say, yeah, that's safe, next. So that machines can look at it and say, yeah, that's safe. So that it's physically, it's impossible it's impossible to express an unsafe configuration. So that's another principle. I'm about to wrap up. Before I do, a word about Waterfall. If this is your first webinar, we've been around for 15 years. We are focused on safe, reliable, efficient operation of physical operations. We're focused on the OT space. We're deployed all over the world, thousands of sites in pretty much every critical infrastructure sector, as well as, lots of different kinds of manufacturing and even building automation, data centers, casinos, these massive buildings, the OT, the power and the elevators and the safety critical and reliability critical systems there, are deploying Waterfall solutions. Waterfall invented the Unidirectional Gateway. This is why, we keep talking about it. This is why we know so much about it. We are trusted by these very large facilities, very important facilities all over the world. This is what Waterfall does. So to wrap it up, I've been talking about network engineering. We're talking about when we need network engineering. Don't get me wrong. Cyber-informed engineering is a coin with 2 sides. We need the whole coin. Cyber-informed engineering is not, let's do all IT security. It's not, let's do all engineering. It's, we have to do both. The coin has 2 sides. We have to do network engineering when consequences are unacceptable. And we do IT security. The sites that I see using network engineering, the sites that I see using safety engineering, the sites that I see using these engineering techniques most intensely are the same sites that do IT security most intensely. It's not one or the other, it's how much of both, which is chapter 8 in my new book, which is launching November 1st. In the email you get, I hope there's a link. Waterfall is giving away copies of the new book as part of the launch promotion. I'm hoping that the email that you get will have a link saying, if you'd like a copy of the new book to dig deeper into network engineering or security engineering concepts, the name of the book is Engineering Grade OT Security. I'm hoping there'll be a link there where you can request a copy, and Waterfall will, try to ship it to you worldwide, give or take, COVID constraints, because shipping and supply chains are still a little bit impaired, but we'll do our best. So that's what I have. We need both IT security and network engineering. It's not one or the other, but people are finally starting to talk about the engineering approach to dealing with cybersecurity in a consistent, cohesive way, instead of just sort of piecemeal the way we've done the last few years. So I'm very excited by the Cyber Informed Engineering Initiative, by the potential for security engineering, in a sense, coming to the rescue, so that we can step off of the IT only track, and the train could zoom on by, and we're still safe. This is what I look forward to. That's what I had. I'm always looking for feedback. Let me know if this is working for you folks. If you're trying these ideas out, I need to know where it works, where it doesn't. And let me offer as well. Waterfall is a product company. We sell product. We sell technology. We don't sell consulting. If you need a Waterfall person to sit down with you and look at your networks and say, how could we do network engineering here? How could we do unidirectional here? It doesn't make sense to do some analog stuff on the safety systems there. Give us a call. One of our experts is happy to sit down with you for a few hours or even a day, no charge, and look at your system and give you our best advice. We're happy to. We provide that service free of charge. That's what I had for you. I hope you found it useful. Natalia, do we have any questions backed up?
Yes, Anders, thank you for a great presentation. We have a few minutes to answer some questions. Our first question is, when I need to send data back into an OT network, how do I do that?
If you need to send data back into an OT network, well, I talked about abstraction. That is one way to get data back into the OT network. That's not a way. That's abstraction is talking about the format of the data, the meaning of the data going in. It should be the data should be as abstract as possible. To actually get the data in, let's say the classic. Well, let's say production orders. We have a refinery that's producing jet fuel, gasoline, diesel fuel, et cetera, and we get orders for 3 million barrels of jet fuel. We got to communicate that order into the refinery. It's not going to execute it right away. We've got a backlog of 10 or 12 days of orders in the refinery. And what does that order look like? It's probably a reasonably abstract XML file coming from SAP or the Oracle ERP. How would that go in? Well, to a man with a hammer, all the world's a nail. To a man with a firewall, all questions have the same answer. Open a TCP port. You need production orders to go in, open a TCP port. You need antivirus signatures, open another TCP port. If you ask Waterfall, we try to give you the most secure answer to every question. So for that question, how can I get production orders in? Do I need them to flow in continuously, second by second? Well, no, I've got 10 days production orders queued in the refinery. Well, how can I get them in safely? Use the Waterfall flip. This is a variation on the Unidirectional Gateway. It can only send one way, but there's a button on the front. If you press the button, it is as if the unit picks up, flips over, and sets down. It can be one way out or one way in, but never both. There's only one transmit circuit board in the device. It can only send one way. So what do? Well, you can press the button. Most people, there's a little timer inside. They set the timer to say at 2 in the morning and at 2 in the afternoon for 10 minutes, flip, and then flip back. What do you do in those 10 minutes? The software does not sit there waiting for something, saying, here, send this through. The software says, oh, look, it's time, reaches out to SAP or Oracle and says, give me production orders, and gets 4 new production orders, sends it through the one-way hardware, and then shuts down, and eventually the hardware flips back. So this is a way to do disciplined updates, disciplined schedule updates. What does discipline mean? It means that the device is designed to frustrate TCP. What's the modern attack method? It's, get a TCP connection to a command and control center, maybe daisy chained through IT, daisy chained through a DMZ. and send commands into the malware, see what works, get the responses back, say, let me try something else, and operate the malware remotely. This takes away that capability. You can't run TCP through the device. It can only send one way. So this is a way to, this is one example of network engineering designs that are, covered in the new book that talk about how can you get information as safely as possible into the network. I hope that answers the question.
Great, thank you. Another question we have is, what are your thoughts on integration on glass for SIS and control system, like through WATEC or Barco?
Short answer is I don't know. I'd have to Google that. I've never heard that term. So, I learned something. Something I haven't mentioned, I co-host the Industrial Security podcast. Waterfall sponsors it as a public service. It's not about Waterfall. It's about our guest. I have not had a guest talking about WATEC or Barco integration on glass. I don't know what that means. When I started the thing, I thought I knew more than I did. I figured there might be 20 or 30 episodes in there. There might, how much is there you can talk about in industrial security? Well, we're on episode 110. Every episode I've learned something. It's been a really humbling experience. So here's another example of something Andrew doesn't know. Let me do some Googling. Let me get back to you with an email. Sorry.
Okay. There's a question about the cost of the one-way security gateway, roughly. I guess that would also be.
Yeah. So the answer is as far as the cost of the gateway goes, the answer is it depends. The Waterfall pricing model, there's a price for the gateway. You buy the gateway hardware, and then each of the connectors has a separate price tag. So if you want to make a copy of an Aviva Pi server, there's a price for that. If you want to make a copy of a file server, well, that's a simpler thing. There's a lower price tag for that. Syslog is a lower price tag. You want to make a copy of an Oracle server, there's a higher price tag. So depends on what you need to make a copy of, what kind of data is flowing through the system. But and I'm not gonna put up the price list, but I will say that a typical, Waterfall's on record saying a typical small system, the smallest systems we see routinely are about $25,000 US or euros. And the biggest ones, the most complicated systems are, 150,000 or maybe even a little bit higher euros. That's the range. And so, you might ask, I've had people say, whoa, that costs way more than a firewall. Well, two things. One is, depends on what firewalls you're looking at. Some of them are very expensive. Two is, there's a lot of labor with a firewall. Getting the firewall configured is going to be more than half the cost of deploying a firewall, whereas configuring a gateway is almost nothing. There's like 4 screens for a lot of these connectors. And the third is, really, I was touring a facility about a month ago, and they pointed out a big cabinet. And I always thought, the PLCs I'm familiar with are like this big. That's a PLC with a bunch of. No, they said that whole cabinet is one PLC. I'm going, wow. What's that cost? A fully fleshed out cabinet is, between $50,000 and $75,000. Wow. How many of these do you have in the system? About 60 or 70. So you've got between $3 and $5 million in PLCs deployed. Just PLCs, forget the physical process, just the automation. Yeah. And, if you need to spend an extra $20,000 or $30,000 on network engineering to prevent anything bad coming in and causing a truly unacceptable consequence, is that an acceptable cost? Sure it is. That's less than we spend on one more PLC. So the cost is acceptable. Cost should not be a factor. What does your safety system cost? Do you have budget for a safety system? Of course we do. If the consequences are unacceptable, the engineering community is required to defeat, to prevent those consequences to a very high degree of confidence. Engineering grade means deterministic, means mathematically modelable, does not mean perfect, does not mean 100.00%, but it means we understand the failures, the potential failures really thoroughly, and we've taken steps to reduce them to an acceptable level. And we have very high confidence in the numbers of reducing, those failure possibilities. So we need engineering grade protection for safety. And when safety consequences are unacceptable, when unacceptable consequences are possible, we don't ask, what's a safety system cost? We say, we got to do this, or it's not going to work. If you're talking, Natalia, you're on mute.
No. Thank you, Andrew. Well, we reached the top of the hour. Do you want to take one more question and we'll wrap up?
If you have one more, go for it.
Sure. Are there standards out there that talk about network engineering?
The term network engineering is one that I've coined in the new book. I haven't seen other people talk about network engineering. I've seen a lot of people talk about these techniques. And one of the things I'm trying to do in the new book is pull techniques together and give them a name so that we can talk about them sort of as a unit. So no, there's no standard out there that uses the phrase network engineering, but every one of the techniques I'm talking about is out there in some standard or another. So, for example, what standard talks about unidirectional gateways? Well, it's there in the NIST 882 standard. The French ANSI standard, Agence Nationale du Système d'Information, de Security d'Information, ANSSI, not the North American ANSI standard, the ANSSI critical infrastructure standards for industrial cybersecurity. There is an English version of them if you Google on the internet. It's 2 volumes. Detailed measures and classification method. They talk about, the classification method talks about organizing networks into 3 classes of consequences. They don't use the word consequences, they use the word class. But they're, primarily 90 or more % of the calculation is calculating consequence. So their class 3 networks I think of as safety critical. Their class 2 networks I think of as reliability critical. And their class 1 networks I think of as they're actually defined in the standard as business networks. Business networks by definition are class 1. And what the standard says is between class 3 and class 2 networks, it's illegal. This is a regulation, not a standard. It's illegal to put a firewall between a safety critical and a reliability critical or a business network. You must use unidirectional gateways or an air gap. Those are your choices. Between a reliability critical network and a lesser network, like a business network, at that consequence boundary, you are allowed to use firewalls, but it's discouraged. They strongly encourage unidirectional communications. They strongly discourage remote access at that boundary into critical networks. A small shoe factory, you need remote access. 2-factor, go wild. You need remote access into a 2 gigawatt power plant that is critical to the grid. They strongly discourage remote access. So yeah, there's standards out there that talk about these techniques, but what I'm trying to do in the new book is sort of pull them together into a single body of knowledge and give the body of knowledge a name so we can start talking about it instead of scratching our heads about individual X, Y's, and Z's. But if that was our last question, let me use the opportunity. Thank you, Natalia, for leading us through this, and thank you everyone for attending. I hope you got something out of it. Give us some feedback, and like I said, call on us if you'd like a free consultation. If we can help in any way, this is what we do.
Thank you, thank you, Andrew. On behalf of Waterfall, we'd like to thank you for joining us today, and we'll see you next time. Thank you, everyone.